In today's class, we will address the issue of energy release. Whenever we have been talking of explosions, what did we say? At some point or at some source, some energy E naught gets released, and what we ultimately get is, if the energy release is spontaneous, we get a blast wave which does the particular damage. Therefore, the essence of an explosion is that the energy should be released, and that too it must be released fast enough. Therefore, today we will take a look at how to determine energy release, and we consider one specific example or one specific case. We look at the energy release in the case of some substances which can undergo chemical reaction. Such substances which can undergo chemical reactions are also known as explosives. Let us first be very clear what we mean by an explosive, and for that we will take a few examples. Let us consider a substance, let us say like hydrogen gas. Let us say I consider hydrogen gas and it is available in the market in cylinders. The cylinders are filled, here you have a regulator, the cylinder is filled with hydrogen gas, and whenever we want hydrogen gas we tap it from the cylinder. Well, the hydrogen gas we say is little dangerous, handle it carefully. But if I were to take this hydrogen gas into this, if I take this example of hydrogen gas, I put an electrical spark in it or I heat it, nothing is going to happen. The hydrogen gas is not going to react and generate a large volume and generate an explosion, because it is just a fuel. It is just a fuel which by itself cannot react and form products of combustion, and these products cannot really go to high temperature. Even if I heat it, only the sensible heat of hydrogen is going to increase. Maybe a similar example I can say, well, I go to the market and buy kerosene, maybe I buy kerosene oil in a pail, let us say. If I isolate this kerosene oil, let us say kerosene oil, if I isolate it from the air and heat the oil, nothing is going to happen, only maybe it will vaporize, but unless it mixes with air and then reacts with air, then only some combustion or an explosion can take place. Therefore, we say, well, a fuel or a substance like fuel like hydrogen, maybe methane, ethane, any substance you take are not really substances which are explosive. Therefore, we talk in terms of fuels, and these fuels could be either a gas, like we talked in terms of hydrogen gas, we could have maybe methane, ethane, could be a liquid, could be a volatile liquid like petrol, maybe kerosene. It could also, you have solid like you have wood, but wood contains little bit of oxygen, we will take a look at it. Maybe these are the substances. Let us take an example. We talked of the largest man-made explosion. We said this happened in the Ural mountains in Siberia around June 4, I think it was 1979 or so. What really happened in this case? You had the pipeline which was conveying natural gas is nothing but methane. A huge spill took place, that means the rupture in the pipeline over a long distance happened, and lot of this methane got spilled over, gaseous methane, and you have low temperature methane gas. And what happened? Along the ground, the methane gas just kept on traversing. Nothing really happened in this particular explosion, because methane just kept hugging the ground and kept on traveling, because the wind took it across. And what really caused the explosion? Maybe we said that you had the Trans-Siberian Railway, that means you have a double track railway trains going in opposite directions, and it so happened unfortunately that two trains were passing through this cloud of methane gas at the same time in opposite directions. And when these two trains were passing in opposite directions, they introduced turbulence, they introduced mixing with air, and along with mixing of air you had an ignition source, like you had the spark from the overhead cable, and that caused a giant explosion. And we said this particular explosion decimated the vegetation around this particular place of the explosion. Therefore, we say, well, in this case you had methane, and methane is just a fuel, it cannot burn itself. I need air to be able to form a combustible substance, and we define an explosive as a substance which contains fuel and an oxidizer with which it can react and form products of combustion which are at high temperature and probably at high pressure, with which an explosion can get started. Therefore, let us now take a view on this. Well, it need not be only a gaseous fuel like methane and air, it could be any substance. Therefore, let us take a look at different types of explosives. We talked in terms of Texas city disaster. Well, this happened around April 1947 or so, and what happened in this case? You had ammonium nitrate. What was the formula for ammonium nitrate? NH4NO3. The ammonium nitrate was stored in bags in the hull of a ship, and it started reacting spontaneously. How can a substance start reacting? It started reacting slowly, and all of a sudden the reaction built up. Therefore, if you look at a substance like ammonium nitrate, it is not a mixture. It is not a mixture like methane and air, or you have hydrogen mixing with air to form a combustible. It is a compound, it is a homogeneous compound. And what is happening, if you look at this particular compound, if I take a look at it, well, I have 2 nitrogen molecules, 2 nitrogen atoms, I have 4 hydrogen atoms, and I have 3 oxygen atoms. Therefore, it is quite possible, maybe the nitrogen atoms, let us consider for the present it is inert, and the 4 hydrogen atoms can react with 2 oxygen atoms to form 2 H2O, that means 2 water molecules, and we are left with 1 oxygen atom. Therefore, it is quite possible that the hydrogen in the ammonium nitrate can react with oxygen in the same ammonium nitrate and form a chemical reaction which can generate energy, and therefore, we say, well, ammonium nitrate could be an explosive. Therefore, explosives are those substances which contain fuel and oxygen within this particular substance. It could be a mixture of 2 things. Maybe I just mix some solid oxidizer with a solid fuel, I mix it, that is, it is heterogeneous. It could again be an explosive, or it could be a chemical compound in which fuel and oxidizer are intimately mixed. Therefore, whenever we talk of an explosive, we mean, well, I have fuel and oxidizer which are present. If I consider only a fuel, well, the fuel has to get out, find air, like in the explosion at Ural Mountains, wherein maybe methane had to get mixed with air to form an explosive. That means, initially I just had fuel, and then I formed this mixture, which if ignited forms the products of combustion, and we are interested in finding out what is the energy release in the particular explosion. Let us take one more example to make sure we are on the right track. I take the example of the accident at Flixborough. I was particular to take this example because many of you would go and work in chemical plants in the future, or in some plants which handles chemicals. And what happened in this particular plant? There was a major disaster. I think it was around June 1, 1974. What happened in this case? The Flixborough plant, this is in UK, was making some intermediate known as caprolactam, and this intermediate or a precursor is used in making nylon. How do you make this precursor caprolactam? You have in a chemical plant, you have these reactors. There was something like there were 6 reactors, one after the other. Let us say you have 6 reactors. And what happens? Maybe what they used is cyclohexane, maybe we are talking of hexane, C6, H14. in the cyclo mode. That means it's not normal heptane, but it is in a cyclical chain. And what is done is this particular hexane, or we say, well, it gets oxidized and you keep on oxidizing it in the different reactors until you form, say, caprolactam, which is used for making nylon. Therefore, you have these different reactors, and what is done is from one reactor, the substance goes to the next, it gets oxidized, again it goes to the next, it goes to the next, it goes to the next, and this is how, and ultimately you get whatever you want. In this particular case, this particular cyclohexane was being converted to hexanol, hexanone and stuff like that, and let us not get into too much of these details. But what happened is, a few days before this explosion, you have something like 6 reactors, the reactor number 4 developed a small crack. And therefore, what was done is, you have a number of reactors, you can always do without one. Therefore, what was done was, this reactor was shut off, and the product from this reactor was connected through a bypass line to the next reactor, that is, from 3rd reactor it goes to the 5th reactor. This bypass line is something between 0.1 to 0.2 meter in diameter. Well, during operation, this particular bypass line developed a crack, and the hexane or the cyclohexane or hexanol which leaked into it, something like the leak was so rapid that something like 40 tons of cyclohexane leaked out. This was because the reactors are essentially operating at high pressure. In this case, it was operating at a pressure of 10 atmospheres, and the temperature here was something like 145 degrees centigrade. Therefore, what happened is 40 tons of cyclohexane leaked out, and you form a huge cloud, a cloud of cyclohexane mixes with air, you form a mixture of hexane and air, and the size of this cloud was something like between 100 meters to 200 meters diameter. That means it is a huge cloud of this vapor mixture which is formed, which is now an explosive, because you talk in terms of hexane C6H6, it is mixing with air, and air contains oxygen, air contains nitrogen. We will take a look at the proportions a little later, and therefore, in presence of the vapor of cyclohexane, that is hexane and oxygen, it can react and you form this cloud of the explosive. And when it found, in a chemical plant you have furnaces and other things which are always hot, it finds an ignition source maybe in a furnace or in some hot spot, and the whole thing just released the energy, and the magnitude of energy release was so high, it was something like 60 into 10 to the power 12 joules of energy got released. And this is what we are interested. We want to find out, when I have an explosive, a given quantity of explosive, how much energy is getting released. What is it we have done so far? We know, once I know how much energy is released, and this is what we have done, we say, well, E naught I know, therefore, I can calculate my explosion length being E naught by P naught to the power 1 by 3, and in this case with 60 into 10 to the power 12 and P naught being 10 to the power 5 Pascal, the value is something like almost like 80, it will come out to a few 100 meters, something like 180 meters or so. And if I am interested in the overpressure due to this explosion taking place, and it was told that this explosion was so strong that this township of Flixborough, at a radius of something like almost 2 kilometers around the site of the explosion, was devastated, buildings got totally damaged, and therefore, using this value of R naught and maybe at a distance of 2 kilometers, that is 2000 meters, I can find out the value of Rs by R naught and then determine the value of overpressure, which we now know how to do. We know how to calculate the impulse, and we also know how to calculate the fragments which are thrown off. Therefore, what is primarily required is the energy release from such explosions, and this is what we do today. Therefore, let us come back to our problem. Therefore, we say, well, in any explosion, the first thing required is how much energy is released in an explosion. Let's try to find that out. How much energy is released? we are talking of energy released in a chemical reaction, and therefore, maybe we tell ourselves whenever we talk of chemical reactions, what is the chemical reaction we are talking of in the Flicksborough? We say, well, C6 H14 hexane plus maybe air forms maybe products of combustion, could be carbon dioxide, could be carbon monoxide, could be water, could be anything else, could be nitrogen substances, maybe this hexane, I should have said normal hexane is C12 H14, C6 into 2 into 14 H14, let us say H14 plus air is products here. And therefore, what is it we are talking of? We must remember, see we cannot talk in terms of units of mass. We say when for this particular reaction, we say, well, 1 mole of hexane reacts with 1 mole of air to form, let us say, 1 mole of products, 1 into this, 1 into this, 1 of this. But therefore, in a chemical reaction, we use the terminology moles. What is this mole? Why do not we use the unit of mass? Why do not we say so much kilogram reacts with so much kilogram to create products which are so much kilograms? It is possible to use, but what is this mole? Let us first introduce the concept of mole, because when we see rate of reaction, we will again see mole is not the apt term to use, maybe we should use something like concentration. But what do we mean by mole? Let's put things more clearly. Whenever we say mole, what is it we mean? We have a quantity of matter. Let us say I have some amount of hydrogen. Let us say I have something like 4 grams of hydrogen with me in a particular bottle. That means I have a certain quantity of hydrogen, and how do we define mass? Mass is the quantity of matter in a particular body. Therefore, when we say yes mass, we mean quantity of matter, quantity. Well, when we say mole, it also talks of the same thing, it also talks in terms of quantity of matter, but instead of talking in terms of kilograms or grams, we say in terms of molecular mass. What does this mean? Supposing we say hydrogen has a molecular mass, and we know molecular mass of hydrogen is 2 grams per mole. Therefore, to describe the quantity of matter of contain 4 grams of hydrogen, I just tell myself the number of moles of hydrogen is 4 grams divided by 2 grams per mole, which is equal to 2 moles. Therefore, mole is also a unit which describes the quantity of matter. Well, I go to the market, I want to buy, let us say 1 kg of potato. I need not, the quantity I want to buy is 1 kg. If I say that the molecular mass of potato is something like 2000 gram per mole, I can as well tell the shopkeeper, maybe if he is smart he will understand it, I can say I need to buy 1000 divided by 2000 moles of potato, which is equal to 0.5 moles of potato. Therefore, all what I am saying is moles is just a unit of the quantity of matter in a substance, and this quantity moles helps us to write the chemical reactions, and it is a useful tool while studying chemistry of substances. Therefore, we will in the course of today's lecture and next 2 or 3 lectures confine ourselves in describing the quantity of a substance in terms of moles. We will also see in terms of volume, in terms of mass, but what we do is, let us say, moles. By now the definition of moles must be clear. Let us say I have a reaction, just to make sure we understand it, in which maybe hydrogen reacts with oxygen to form, let us say, oxygen molecule to form, let us say, water. I tell, well, this equation is not balanced, I just wrote hydrogen reacts with oxygen to form water. Now, in this reaction I say 4 grams of hydrogen reacts with, let us say, some substance may be 32 grams of hydrogen to form, let us say, 32, mass must be conserved, it forms 36 grams of water, 32 grams of oxygen to form 36 grams of water, because mass has to be conserved. Now, how do we write this equation? Well, if in terms of moles, I have 4 divided by 2 gram per mole, that is 2 moles of hydrogen. I have 32, oxygen is 32 grams per mole, that is 1 mole of oxygen. I have 36 grams of water, 36, and H2O has a molecular mass of 2 plus 16, that is 18 grams per mole, that means 2 moles, and therefore, this equation I can write as 2H2 plus I have 1 mole, that is 1 of O2, gives me something like 36 divided by 2, that is 2 moles of water. And this is how we write a chemical reaction. That means, we write in terms of moles, and this moles has an advantage, it is much easier to use than to write a chemical reaction in terms of moles rather than to write in terms of masses, and we will use this unit of moles while talking in terms of chemical reaction. Now, from when we talk of moles, it is also necessary to distinguish the word mole from molecules. When we say molecules, we have any substances, and any substance, let us say I have a quantity of a substance over here, it contains of lot of molecules, small molecules which are interacting with each other in the substance. Therefore, one particular mole, if I say 1 mole of a substance, it contains the Avogadro's number of the molecules, that is 6.023 into 10 to the power 23 molecules. Let us not confuse the word between molecules and moles. Well, 1 mole consists 6.023 into 10 to the power 23 molecules, which is known as Avogadro's number. There is one great advantage in working with moles. If we consider in terms of a gas, let us consider an ideal gas. We say, well, an ideal gas is described by the equation PV is equal to mass into specific gas constant into temperature. If we want to express, instead of moles, instead of mass over here, so much kilogram, specific gas constant is in joules per kilogram Kelvin. Supposing I were to write in terms of moles, therefore, I can write this equation PV is equal to the number of moles into the universal gas constant R naught into T, where R naught is the same for all gases and it is equal to 8.314 joule per mole Kelvin. Therefore, I do not need to go back and find out the specific gas constant for each gas and then relate the mass and the volume. Rather, if I write in terms of moles, I can use the gas constant, that is the universal gas constant, to relate volume and temperature with respect to the moles over here. Therefore, from this definition it also works out, if I consider the standard temperature and pressure conditions, namely 1 atmosphere pressure, maybe a temperature of 25 degrees centigrade, which we call standard temperature and pressure. If I were to say what is the volume occupied by 1 mole, that means V is equal to volume occupied by 1 mole over here into R naught 8.314 joule per mole Kelvin into temperature 25 degrees centigrade plus 273, 298 divided by something like pressure comes over here, pressure is 1 atmosphere, that is 10 to the power 5 Pascal. Well, the volume which comes out to be equal to 0.0224 meter cube. That means, the volume occupied by 1 mole of a gas of any gas at standard temperature and pressure is something like 22.4 liters. And these things will be useful for us when we do the calculation. Therefore, to begin with discussing about energy release, we must first be very clear that we will like to use the terminology moles instead of maybe mass, instead of describing the quantity of a substance as meter cube, we will like to use moles for description. Having said that, let us go forward. Let us try to see why should energy be released in a reaction. You know, we tell ourselves, well, what did we say? I have, let us say, N1 moles of a fuel with N2 moles of an oxidizer, let us say oxidizer, I do not know what this oxidizer is, could be oxygen, it could be chlorine, it could be any other oxidizer. Let us say it forms N3 moles of some products. I am interested in finding out what is the energy release. Now, this has fuel and oxidizer, therefore, it becomes something like an explosive, and I want to find out how much energy is released in this particular reaction. Therefore, what is it I do? Well, I realize if energy has to be released, you know, this substance has some energy by itself, you know, any substance. Like I take this piece of duster which is wood. Well, wood also contains carbon, hydrogen, oxygen, stuff like that, and it also contains some energy, some innate energy, some internal energy, and therefore, we say, well, any fuel substance will contain some inherent energy. And where does this inherent energy come from? Well, it has all these bonds which are there, maybe you have all these bonds of carbon, hydrogen, oxygen, or whatever it is, it has all these structure and it has some energy which we could call as internal chemical energy. Let us call it as ICE, internal chemical energy. So, also when I consider, that means N1 of fuel has certain amount of internal chemical energy, the N2 moles of oxidizer has also some amount of energy which I call as corresponding to oxidizer. This corresponds to fuel over here, and then the products, you know, when I react fuel with oxidizer, I get products of a different structure. Well, it could also, this could also contain some internal chemical energy, let us say of products. Now, if I look at the structure and find, well, the internal chemical energy of products, let us say, is 200 some units for the total of the N3 moles. If the internal chemical energy of the oxidizer is, let us say, 50 joules over here for the total, here it is 200 joules for the products over here. If for the fuel it is, let us say, 120 joules over here, the total internal chemical energy of the fuel and oxidizer in this particular, for these particular moles, is 170 joules. In this case, well, my internal chemical energy is 200 joules, which means, well, energy cannot be liberated in this, and only what has happened, for this reaction to go on, I must supply some energy which is equal to 30 joules, such that I get the net energy, because energy is conserved, energy cannot be cannot just be picked up, and it is something which is conserved in a chemical reaction, or in universe, maybe we say, well, that is the first law of thermodynamics, energy is conserved, and therefore, we say for this reaction to take place, I must supply some energy. But supposing the internal chemical energy of the products were something like, let us say, 100 joules, then what is happening? The internal chemical energy of the reactants, that is the fuel and oxidizer, was something, let us say I put energy on this scale. Well, I put a time scale over here, let us say T. Initially, I have substances which are just reactive, the total energy was 170. Afterwards, when things got completed, well, the energy is something like 100 over here. Therefore, I get this energy which is released, and this is the energy from the chemical reaction. Therefore, we find that when the internal chemical energy of the total products is less than the internal chemical energy of the substances which react, or reactants which we call, if this is less than this, well, some energy is released, and therefore, I can write the energy release in a chemical reaction. That means, let us say, energy release in any chemical reaction, E naught or E is equal to internal chemical energy of all the products put together for all the moles which are formed, minus the internal chemical energy of the reactants over here. And to be able to deliver energy, well, it must decrease, or rather energy in joules is given by negative of ICE for the products minus the internal chemical energy of the reactants. Well, this is how we should do, therefore, we must be able to find out what is the internal chemical energy, and a terminology what is used to denote the internal chemical energy is what we call as the heat of formation. That means, we would like to use terminologies which are more capable of being defined properly. Therefore, we say a substance is characterized in terms of heat of formation. I will say, well, I call this as delta enthalpy of formation at some condition, we will say call it as heat of formation. And how do I define it? Well, it implies something like the internal chemical energy, and how do I define it? Well, I say heat of formation of a substance is the heat required, let us put it down, heat required to form 1 mole of a substance from, or 1 mole of a substance at standard condition, that means at 1 atmosphere pressure and 25 degrees centigrade. That means the heat required to form 1 mole of a substance at 1 atmosphere pressure and 25 degrees centigrade from its naturally occurring elements. Again at 1 atmosphere and 25 degrees centigrade. Therefore, we define heat of formation as the heat required to form 1 mole of a substance at the standard conditions from its naturally occurring elements, again at the same standard conditions. And therefore, the notation is the additional heat which is required for forming a substance at the standard conditions when the elements or the naturally occurring elements are again at the standard condition. Therefore, this is where, and this is same as the internal chemical energy. Let us therefore say, we can therefore now say, well, the energy liberated in a chemical reaction is equal to the net heat of formation of the total products minus, let us say products, minus the net heat of formation of the reactants for all the molecules you put together, all the moles you put together, you get the energy release in a reaction, and we say in this reaction so much joules is formed. Therefore, I think we must take some examples of how we define heat of formation, and what is done is, it is defined with respect to the naturally occurring elements. And what are these naturally occurring elements? Let us put some of them down over here. For instance, in nature oxygen occurs as a gas, maybe nitrogen is available as a gas, maybe carbon is available as coal or charcoal, maybe carbon as a solid, oxygen as a gas, maybe nitrogen as a gas, and so on. Different types of elements occur in nature. Supposing I want to form, let us say nitrogen, I could also have hydrogen as a gas which occurs in nature. Therefore, if I am interested in forming water and I want to define what is the heat of formation of water, then I am interested in forming water, but water I cannot say 1 atmosphere pressure. I just say if I want to form water at 25 degrees centigrade from its elements, namely hydrogen gas which occurs in nature, oxygen gas which occurs in nature, or rather H2 as a gas at 1 atmosphere pressure and 25 degrees centigrade, oxygen as a gas at 1 atmosphere pressure and 25 degrees centigrade, I form water, that means water as a liquid at 25 degrees centigrade. The heat required to form water from hydrogen and oxygen again at the same condition as water which is formed is what we call as heat of formation of water, H2O liquid. Therefore, let us take a look, and by very definition, since we are defining a substance in terms of elements, the heat of formation of the elements are 0. Therefore, heat of formation of an element like let us say hydrogen gas at the standard condition 1 atmosphere pressure and 25 degrees centigrade is 0. The heat of formation of let us say oxygen gas at the standard condition is 0, and therefore, all these elements, let us say carbon exists as a solid, heat of formation of carbon at the standard condition is 0, and we have to evaluate the heat of formation as the heat required to form 1 mole of water from its elements, namely hydrogen and oxygen, is what is called heat of formation of water. Therefore, let us try to evaluate this. We need to go and build up a table of heat of formation, and it is given. It is all these things are available as tables, but we must know how it comes from. Let us take an example. We take the example of, let us say, carbon dioxide. I want to form, let us say, the heat of formation of carbon dioxide. We tell ourselves, well, this is a substance, carbon dioxide, therefore, I have carbon as a solid and it reacts with oxygen as a gas. Let us say I form carbon dioxide as a gas. Therefore, I am interested in heat of formation of carbon dioxide. Well, I know, well, these are elements, I need to do this, but I also know if I take 1 kilogram of carbon, that means I take 1 kilogram of carbon, I burn it in oxygen or air or whatever it is, I burn 1 kilogram of carbon. The heat which is generated in this particular reaction is something like 32,800 kilojoules. That means, if I burn 1 kilogram of carbon with oxygen to form carbon dioxide, the energy liberated is 32,800 kilojoules. Therefore, if instead of having, that means now I say 1 mole of carbon, if I were to burn with oxygen, that means if I take this particular reaction, according to this reaction 1 mole of solid carbon reacts with 1 mole of oxygen to form 1 mole of carbon dioxide. Therefore, if I consider 1 mole of carbon, well, I know the molecular mass of carbon is something like 12 grams per mole, and therefore, if I say 32,800 kilojoules is produced from 1 kilogram of carbon, from 1 mole of carbon, the amount of energy which is generated is 32,800 from 12, that means into 0.012 is the amount, that means per mole of carbon, this is the amount of energy which is generated, which is equal to, I get a value around 396 or 393.6 kilojoules. That means, to generate 1 mole of carbon dioxide, I need to supply something like when I form this, automatically in this reaction 393 kilojoules of heat is getting generated. Therefore, what does this heat do? It increases the temperature of carbon dioxide to a high value, because heat is getting generated, therefore, the gases are at high temperature. But mind you, when I talk of heat of formation, I am talking of heat of formation of carbon dioxide at 1 atmosphere pressure and at a temperature of 25 degrees centigrade. This is the standard condition, and therefore, I have to cool this gas, that means the hot gas has to be cooled, and therefore, when I react carbon with oxygen, so much heat is getting generated, I have to remove so much of heat to bring back the carbon dioxide to its natural condition. Therefore, in this particular reaction, I have to subtract something like 393.6 kilojoules of energy to be able to get back the carbon dioxide in standard condition, and therefore, since I remove the heat, I say the heat of formation of carbon dioxide is equal to minus 393.6 kilojoules. And this is how the values are calculated. Maybe you react the elements together, form the substances. If the substances generate heat, well, the temperature goes up, I have to remove the heat to be able to get back the substance to the original condition, and we say heat of formation of carbon dioxide is 393.6 kilojoules. Let us take one more example. We take a simpler example of something like hydrogen and oxygen being burned to form water. Well, we do the same thing, but it is not as simple as that, we have to apportion things together. Let us say I am interested in heat of formation of, let us say, water. Therefore, I know, well, hydrogen as a gas, 1 mole of hydrogen gas plus half mole of oxygen gas forms 1 mole of water, that means as a liquid water, Now, what is it I am now talking of? Well, if I do an experiment and in my experiment I have something like let's say I have 2 grams of hydrogen I burn with something like here 30 to 16 grams of oxygen. I know that the heat which is generated in this reaction, again it is an exothermic reaction, heat is getting evolved. That means I generate something like 286 kilojoules of heat gets generated in this particular reaction, or rather when 1 mole of hydrogen gets consumed, because 1 mole of hydrogen corresponds to 2 gram, and in this reaction I am talking in terms of 2 grams. That means for every 1 mole of hydrogen getting consumed, I generate 286, or rather when 1 mole of water is being formed, I have an energy which is 286, and if this has to be brought back to the ambient condition, that is the standard condition of 1 atmosphere pressure and 25 degrees centigrade, I have to subtract or remove this heat. Therefore, I tell the heat of formation of water as a liquid is equal to minus 286 kilojoules per mole. And so, we can keep on doing these exercise for the different substances, and let us put down a list of tables and then qualify further. You know, normally these things are arrived at experimentally. We look at the elements in as much as they form a substance, and if the reaction is exothermic, well, I have to remove the heat to be able to form this substance at the standard condition. If it is endothermic, well, I have to supply the heat, and in which case the heat of formation would be positive. And if I put some of the values down, let us put a few values down such that we get a feel for how to use it in case of chemical reactions. Let us put a few of them together. Let us say I have methane CH4. The heat of formation of methane is minus 74.9 kilojoule per mole. Therefore, we are talking in terms of energy per mole. I take from methane, I go to ethane C2H6. The energy or heat of formation is equal to minus 84.7 kilojoule per mole. I go to propane C3H8. The heat of formation is minus 103.9 kilojoule per mole. I come to the last category. You know, these are all alkanes: methane, ethane, propane, maybe butane, C4H10, and so on it goes. We'll stop with these hydrocarbon chains with this minus 124.7 kilojoule per mole. If I take a more longer chain, like I say kerosene, which is something like normal dodecane. Dodecane means C12H26, which is kerosene. The heat of formation is higher at minus 292.9 kilojoules per mole. How do I determine all this? Well, we just now told ourselves, well, I will react carbon at the standard condition of 25 degrees centigrade with, let us say, hydrogen gas at 1 atmosphere pressure and 25 degrees centigrade, and maybe depending if I want methane 1 with 2 moles of this to form CH4 over here, I form 1 mole of this. I find, well, if heat is liberated in this reaction, well, I have to subtract it to be able to form this. Therefore, I get minus 74.9. If I want to form something like CnH M over here, well, I have N of C solid plus M of M by 2 of H2 gives me C of N into Hm, for which I can do this particular reaction or a combination of reactions and find out the heat of formation. This is how it is done, and these are the values which are reported in literature. Let us take one or two more substances. Well, we take acetylene, and what is the difference? See, these are all alkanes, this is alkyne, acetylene is C2H2, and the structure of these substances were quite simple. We have CH H4, we have Cc H6 over here, these are the hydrogen atoms which are attached to this, we have C3 H8, we have hydrogen bonded to this and so on, but when it came to acetylene, we had something like a triple bond and then we had H and H over here C2H2, and in case of acetylene the heat of formation is positive and it is equal to plus 226.7. Well, what is it we see from these tables? We will just take a look at this and proceed with heat of formation of one or two more substances. We find as the substance increases in complexity, that means as the bonds keep on increasing, well, the heat of formation becomes more and more negative. That means maybe kerosene has a much higher value, but it is a more negative value than maybe methane. We also find as the molecule becomes more complex, this is a gas, this is a gas, this is a gas, but it liquefies a little earlier. Well, this becomes a volatile liquid. Maybe as a substance increases in complexity, it also from a gas phase it also exists as maybe a kerosene liquid. I go to naphthalene and naphtha which exist as solids, and therefore, we see that as the substance becomes more complex, well, the heat of formation becomes more negative, but has a higher value. In the case of acetylene, which is a triple bond, well, I have to supply heat. That means compared to kerosene, which in a reaction to form kerosene I generate heat, in which I have to supply heat, therefore, a lot of heat gets locked into it, and therefore, acetylene is a gas which is used in welding, but it is quite strong, it can releases energy spontaneously, it is a very strong explosive. Maybe we will take a look at this a little later. Let us put down one or two more values of heat of formation before I go back and learn how to apply it, and also we see what is the meaning of all these things. Let us take two more substances. Well, I have water, I have heat of formation of water. We just now were telling it is equal to minus 286.7 kilojoule per mole. Heat of formation of carbon dioxide at the standard condition, mind you, it is all standard condition, is equal to minus 110.5 kilojoule per mole, and heat of formation of carbon dioxide is equal to minus 393.5. Therefore, these are these things which are available in literature, and how do? We do in experiments in which we find whether heat is generated while forming these substances from the naturally occurring elements, and then we put these values down. But it is also possible to calculate these things, and why do we say that? When we talk of the internal chemical energy of a substance, what is it we mean? We mean the energy associated with the particular structure. We say methane has these particular bonds in which carbon is associated with the bond over here. Therefore, it is possible to express the heat of formation in terms of the bond energy or the structure, the energy of the structure of the particular molecule. Therefore, let us say I am interested in heat of formation of water. If I want to find the heat of formation of water, well, water is H2O, it consists of O, H and H, it consists of two OH bonds. And how is water formed? Well, I consider the hydrogen molecule which has HH bond. I have half a mole of oxygen, 1 mole of oxygen has this particular bond, and what is it I form? I form two OH bonds over here as water. Therefore, if I were to determine the heat of formation of water, see I define heat of formation as the heat required to form 1 mole of a substance at standard conditions from these elements again at standard conditions, and therefore, now I put some energy here, I put some energy here, that means the heat of formation I have to bring these things back to the datum value, or rather I must be able to write heat of formation of the product, which is water here, is equal to the bond energy what is available to me for the structure. That means, I have 2 of the OH bonds are available, minus I have the energy, that is the bond energy of HH atom, plus I have half a mole, that means half bond energy of this particular one. And these bond energies of maybe a OH bond, maybe HH bond, maybe the OO bond are all available in literature. These chemists have determined the values of these bonds, and let us take some values. If I take the value of the hydrogen bond, the OH bond has an energy of 464 kilojoule per mole. The HH bond has an energy of 436, whereas the OO bond has an energy of 499. Therefore, if I were to take a look at heat of formation in terms of difference in bond energy, what is it I get? The heat of formation can be calculated from these bond energies as equal to, I have 2 OH bond, that is 2 into 464, minus I have 1 HH bond, that means equal to into the value of 464, and I have half of this, that means plus I have 499 divided by 2, and this is the heat of formation. Therefore, what is happening is, therefore, I will get the heat of formation of H2O, but when the bonds are being formed, the water is, the hydrogen is a gas, the oxygen is a gas, we are talking of heat of formation of water as a gas. Therefore, I also have this gas has to be converted to a liquid. Therefore, I have to add the latent heat of water, which is equal to, let us say, H per mole of vapor to liquid, and the value is something like 45 kilojoule per mole is the latent heat of vaporization. Plus, I also want to bring down the water to or want to bring down the water at 100 degrees centigrade at atmospheric pressure to 25 degrees. Therefore, I have Cp into something like the from 100 degrees centigrade, I have to reduce it to 25 degrees centigrade, and if I put all these things together, I will get the heat of formation of water to be given by something like minus 280 or so. But we must remember, calculating from bond energies is not very correct, because it is not only the bond energy which exists for a particular molecule, but a molecule will also have vibrational energy, it could have resonance energy and so on. And but what we do is, we use the values which are available in literature, but all what I wanted to tell was heat of formation being the internal chemical energy of a substance can also be derived from the bond energies. Well, we now know how to calculate the bond energies or rather the heat of formation, and now we can calculate the heat released in any chemical reaction. Let's put that together for one particular problem. Supposing I say I have a given volume, let us say 1 meter cube of butane gas C4H10, and this butane gas 1 meter cube also is mixed with air in some proportion, and when chemical reactions occur between, that is, I have 1 meter cube of butane gas and air mixed together, and they form products which are, let us say, CO2 and some other substances. Well, I have carbon dioxide which could be formed, I have water which could be formed. Supposing these are the two substances which are formed, I presume they are formed, we must be able to calculate them as we go along. I presume that these are the substances which are formed. I want to calculate how much energy is liberated from this particular volume. And this is what I will do to begin with in the next class, and then we will go ahead and try to find out how to fix the products which are formed. We will define something like a stoichiometric coefficient, we will also talk in terms of fuel rich and oxidizer rich mixture which is being formed, and for these conditions how to calculate the products and then how to calculate the energy release in a chemical reaction. Well, thank you.